Imagine a material that contracts, bends, and stretches just like human muscle, but is powered entirely by flashes of light or changes in temperature. These are liquid crystal elastomers, a class of smart materials that combine the orientational physics of liquid crystals with the stretchiness of rubber. Liquid crystals flow like liquids but keep their molecular orientation. Their rod-like molecules point in the same direction, much like the pixels in digital screens. Elastomers are rubbery networks. They consist of long, tangled polymer chains held together by chemical crosslinks that act as knots to give the material shape memory. To perform work, the liquid crystal molecules must be aligned. If they're random, their movements cancel out. Aligning them parallel programs the material to move. In the nematic phase, molecules are parallel but don't sit in rows. It is like logs floating down a river. They all point downstream but slide past one another. The smectic phase adds structure, organizing the parallel molecules into neat stacked rows like logs loaded in layers onto a flatbed trailer. The cholesteric phase twists the molecules, shifting their angles progressively to form a helix, much like the steps winding around a spiral staircase. Scientists use several methods to align these molecules, including surface anchoring, mechanical stretching, and applying strong magnetic fields. Surface anchoring is like using a microscopic rake. The liquid crystals settle parallel inside microgrooves etched on a glass surface, aligning with the channels. Mechanical stretching is like a tug-of-war. The material is lightly cured, stretched to pull all the molecules parallel, and then fully cured to lock them in place. Electromagnetic alignment uses force fields. Applying strong magnetic fields coaxes polar molecules to line up along the field lines before the network cures. We can also 3D print them. Pushing the gel aimed through a tiny nozzle creates shear forces that align the molecules, letting us print complex motion paths in 3D space. To hold everything together, polymer chains are tied by chemical knots called crosslinks. This network holds the liquid crystal segments in place to allow shape recovery. Inside chain cells, the liquid crystal molecules dangle off the side of the main polymer chain like charms hanging off a bracelet, retaining high freedom to rotate. In main chain cells, the molecules are integrated directly into the polymer backbone, acting as links in the chain that generate much stronger pulling forces. In 1991, chemist Heinz Finkelmann invented a two-step method, letting scientists align the molecules by stretching a loose gel before locking them down with the final cure. The first step mixes the ingredients into a weakly cross-linked gel. It is highly stretchable but has no order yet, letting scientists stretch it without breaking it. Next, the gel is stretched to align the molecules and exposed to UV light. This triggers new crosslinks that permanently freeze the aligned state into place. Modern synthesis uses click chemistry, like thiol reactions. These occur under mild conditions and eliminate harsh solvents, making it easy to 3D print the material. The actuator works by shifting between order and disorder. When the aligned molecules lose their order, the stretched polymer network coils back up, shrinking the material. At room temperature, the molecules are neatly aligned. This molecular order pushes the polymer chains out, keeping the elastomer long and thin. When heated, the parallel order is disrupted. The molecules bounce randomly, letting the polymer chains shrink back to their coiled, relaxed state. This contraction shrinks the material by up to 40%. Once cooled, the molecules realign, stretching the elastomer back to its original shape. Direct heating is low, so scientists added light-sensitive azobenzene molecules. These allow the material to contract wirelessly when hit with flashes of light. This relies on photosimulation. In the dark, the molecules are straight. When UV light hits, they bend into a V shape, disrupting the liquid crystal order. Imagine a line of soldiers standing shoulder to shoulder. If one soldier steps out of line and then sideways, it disrupts the whole formation, forcing everyone to shift. Cells generate massive power. They contract up to 40%, being biological muscle at 20% and generate several megapascals of lifting force. Unlike pneumatics that require noisy compressors or memory alloys that suffer from metal fatigue, cells are soft, silent, and entirely solid state. Currently, the main limit is cost. Custom lab synthesis is complex, keeping prices at use of $100 to $400 per gram and limiting them to research labs. But new thiol acrylate printing processes are driving synthesis barriers down, with mass production projected to drop costs below $10 per gram. By turning molecular order into mechanical work, liquid crystals are driving soft robotics forward. Thank you for watching Layman's Field. We hope to keep bringing knowledge for everyone.